Hi, good evening everyone. My name is Amit. This is week 5 for GATE live sessions for physics. We'll wait for a couple of minutes and then we'll start because people are still joining. Okay, so when is the net exam for physics?
16 September, yeah.
Okay, and when is this usually happens in June if I'm not wrong, right?
Yeah, this is for June. Yeah.
Okay, so the January one is back to January or it still will happen in
December or January it will take second. Yeah.
so they have been streamlined after the COVID disruption.
Yeah. After the COVID, all the system is going to very zigzag.
But now they have resumed, right? If next session is going to happen in January, that means we are good, right?
Yeah. That's good.
Okay. That's very good. That's very good. ठीक है. Just one more minute and then we'll start.
Yeah. Okay. No problem.
Yeah. Cool. All right. Good evening, everyone. My name is Amit. We are going to start now week 5 of GATE and PTL physics live sessions. Um, I'm going to share my screen now. Is it visible? Can you please confirm?
Yes, sir. Yes.
Okay, very good. So this is the second session for Op-Amp. I'll be very briefly going through what we have discussed in last class. If you still have any doubts, please feel free to stop me anywhere. This is just what we went through in the last class, just the basic concepts. So we discussed what is an operational amplifier. We said that it does some operations like comparison, integration. We'll see this today. We'll see this today. We'll see this today. This comparison we saw in last class. It is an amplifier. Here we are interested in primarily voltage, so it amplifies the input voltage. How does it do it? It's a differential amplifier. So this is the typical circuit for differential amplifier on your screen. It has two gains, AD and AC. This is called the differential gain. This is called the common mode gain. If such a differential amplifier, we design a differential amplifier such that differential gain is much larger than common mode gain, and some other we design circuit in such a manner that output impedances are low and input impedance is high, then what we get is a typical operational amplifier, which is denoted as the symbol you see on the right of your screen, where V plus this is called the inverting non-inverting terminal. This is called the inverting terminal because if any voltage is applied here, it will appear at the output with a phase shift of 180 degrees. That's what we discussed. Before it's good to understand how does an ideal operational amplifier look, what are some of the features that we get, because if we understand ideal, then that becomes much easier to understand how does a non-ideal amplifier work. So this is a typical circuit of an internal model of a operational amplifier. We saw this in the last class. So ideally Rn should be infinity, Rout should be 0, and this is what we discussed in the table, that Rn should be infinity ideally. In real it's some mega ohms. Output impedance should be Rout, as we denote, it should be 0. Usually it's a few ohms or milliohms. Bandwidth we'll see in next class. Slew rate we'll also see in next class, and common mode rejection ratio, as I told you, is nothing but 20 log AC over AD. So this AD over AC. So this should be very high. This means AD should be greater than AC, which will give us a very high common mode rejection ratio. Open loop gain is we denoted by G or AOL, which is usually infinity in ideally, but in reality we get a gain of 10 to the power 5. Output voltage we should get infinity, but we get saturated at these values. These are VSAT. plus VSAT or minus VSAT. These are the input voltages. They can be plus 15 volts or plus 10 volts depending. This will be usually provided to you in the question itself. And so this is what a typical circuit, this is a summary of a circuit. It has an open loop gain, non-inverting input, inverting input, the output, and the gain is defined as this is the formula that this is the only formula in fact in op-amp that you need to remember. That's all. Right, so we discussed this comparator in the last class, that if there is no feedback, then the operational amplifier simply compares the voltages provided at the input and at the inverting and non-inverting terminal. If the voltage at plus non-inverting terminal is higher than inverting terminal, then it will simply result in plus VSAT, which is shown here. Otherwise minus VSAT. So we are essentially comparing the two voltages here. Now this is not always note that this will always saturate, this cannot give any intermediate values. This is always saturate plus VSAT or minus VSAT. We usually do not want that. We want some specific value of V out. Let's say I want V out to be 1000 times V in. We cannot do it using this. So that's why we typically use it in feedback for stability. And positive feedback is used when you need oscillators or Schmitt triggers. Schmitt trigger is a very famous example. You should read up on this. And for negative feedback, what we have is positive feedback means output is connected to the non-inverting terminal. So some part of output is fed back to the input, the non-inverting input. If we feed some part of output to the inverting input, we call it a negative feedback. This is where we operate most of our operational amplifiers, because it gives stable output, and our typical examples are integrator and differentiator. This is a comparator which we see, which does not have any feedback. So a simple question can be asked: which of the following circuits use a feedback in operational amplifiers? Options can be Schmitt trigger, integrator, differentiator, and comparator. Comparator does not use any feedback. These three use feedback. Positive feedback is for oscillator. Negative feedback gives stable output. Integrator and differentiator we'll see in today's class. So that was the summary till now. Any doubts, any inputs you have, please let me know. Okay, some people are trying to join, I'll admit that. Okay, so for the people who just joined, I had just revised what we had done in the last session. So I talked about the properties of an ideal operational amplifier, and that we typically use them in feedback, with negative feedback giving a stable output, right? So we'll directly jump into the questions today. These are, again, as I've told you in the last session also, these are very simple questions, just purely based on KVL and one formula. That's it. There's nothing fancy happening in operational amplifiers. It's a very scoring, very easy to understand, very straightforward topic. Okay, so here this question is from 2012, and it says that output voltage has been given to us for as I told you in the last class, whenever a circuit is provided, we check for three things. Let me just add some other people. Okay, so whenever any question is provided, you always check for three things. Can somebody tell me what are those three things we talked about in the last class? Does someone remember? Okay, I'll just repeat myself. I'm audible, right? Just say yes or no.
Yes, sir.
Okay.
Yes, sir.
Okay, so whenever we are provided an operational amplifier, we ask ourselves three questions. Okay, first let me just go through this question. V out is given, and we are required to find the ratio of R1 and R2. This is the circuit that we have been given. Now, for more details on NPTEL lectures, you can go to this link. That's for conceptual understanding. So let's go into the question. First, whenever any question is asked, you must ask yourself, is it ideal or not? If nothing is provided in the question, assume it to be ideal. Nothing is said in the question, we'll assume that the op-amp is ideal. What does ideal mean? This means R in is infinity. This is R in, this is infinity. This means this voltage can be treated as this voltage. This is very important concept. This is called a virtual short. So this voltage is exactly equal to this voltage, and no output current. I output is 0. This is what we had talked about. Okay, right. Okay, so first we check it's ideal. Okay, it is ideal. Second, is there any feedback? Is there any feedback in this question? Yes or no?
Negative feedback.
Okay, any feedback? Yes. Then what kind of feedback? Negative. Now, I told you negative feedback gives stable outputs. Remember this. So we can directly eliminate the questions if something is unstable. So this must give a stable output, right? So with these two steps, we move forward. Okay, let's go forward. This is the question. So V0 has been given as minus V1 plus V2 by 2. Yeah?
I have doubt how to figure out if the op-amp has a feedback or not, or it is negative or positive.
Very simple. Just check the V output. Check this node. Okay. And see if it is connected to V plus or V minus. Simple. Is there a path from here to here or here? So there is a path, correct? Using this resistor, correct? So this is feedback. If output is connected to input by some resistor, capacitor, inductor, whatever, it is a feedback. Okay? Clear? Is it clear?
Yes, sir, but how to figure out it is negative or positive?
Okay, if the output is connected to negative terminal, this is negative, you can see that, right? A negative here. So,
yeah.
So this output is connected to negative terminal. This means it is negative feedback. If it were connected to this, it would have been positive feedback. Okay. So in this question, we are said V0 equal to minus V1 plus V2 by 2, and we are required to find the ratio of R1 and R2. Again, ideal output, so I'll assume virtual short. What does virtual short say? Whatever the voltage is here, it will be same here. So let's assume the voltage here is Vx. So same voltage would be here, Vx. This is very important. We assume the voltage is Vx here. Now, we apply KCL at this node. Remember. So I am applying KCL at inverting input. KCL says current going in equal to current going out. Okay. So current going in would be V1 minus Vx upon R equal to current going out would be Vx minus V0 upon R. This is the input current at this node. So no current can go here. So all the current that is coming here must go through here. Okay. Okay, very good. So I can say R and R get cancelled. So I can write V1 minus Vx equal to Vx minus V0. This will give me V0 equal to minus V1 plus 2Vx. Okay. Okay, now we don't know the value of Vx. We can know the value of Vx. Look at this circuit now. Again, whatever current is coming through here, let's assume it's I1 and this is I2. So now I apply KCL at non-inverting input. What will it say? Incoming current is I1 equal to outgoing current is I2 plus 0. No current can go through here. This is an ideal output. So this is 0. Again, this was 0 plus 0. We get I1 equal to I2. The value of I1 I can calculate using Ohm's law across this resistor. I'll write V2 minus Vx upon R1. This should be equal to I2. I2 is nothing if I apply Ohm's law across this resistor. So it will be Vx minus 0 upon R2. Now solving this, I can get Vx would be 1 by R1 plus 1 by R2 equal to V2 by R1. This will give me Vx equal to V2 times R2 upon R1 plus R2. I have just taken the LCM here. You will take R1, R2. R1 gets cancelled. R2 remains, so it goes here. Now let's put this value in this expression. So we'll get V0 equal to minus V1 plus 2 times Vx. Okay, 2 times this expression, V2 R2 upon V1 plus V2. Very good. So I'll simply write minus V1 plus V2 times 2R2. Oh, sorry, it's R1 plus R2, not V1 plus V2 upon R1 plus R2. Now, let me change the pen. Sorry. Okay, compare these two expressions. Both are expressions for V0, so they should be the same. So I can simply say, I'll write here minus V1 plus V2 by 2 equal to minus V1 plus V2 times 2R2 upon R1 plus R2. This gets cancelled, V2 gets cancelled out, so I get 4R2 equal to R1 plus R2. This implies R1 equal to 3R2. We were required R1 upon R2, so I can simply say R1 upon R2 equal to 3. This is the answer, R1 plus R2 equal to 3, and this is, I think, one of, yeah, so this is option D. Very straightforward question. I'll just summarize a bit. First thing, we notice that this is an ideal op-amp, so no current will go in on the input side and no current will go out from the output side, and there is a virtual short. So I simply applied KCL at this node and wrote this expression. Again, just Ohm's law, nothing fancy. Then I applied KCL at this node and using Ohm's law I wrote this. I got the value of Vx from this expression. I put it here. I got the value for V0 and compared it with the expression given in the question. The rest is algebra and nothing, no calculator required. It's just you can even do it orally. We got R1 upon R2 equal to 3. Very simple, very straightforward question. It was based on a negative feedback. The problem used a negative feedback circuit. Right. Any doubts you have? Any queries? Any comments? Or we can move forward for our next question. Please feel free to stop me, because sometimes it looks like that things are going too fast and you must stop me. That no, like someone just asked me ki, why is it a negative feedback? So that was a good question. It's a very basic question, but very good question. It helps in building up your understanding. All right. Next question. So as I always say, whenever a question is given to op-amp, ask yourself three things. First, is it ideal? So question itself says it's ideal. Very good. So what does an ideal op-amp mean? It means current is 0, I equal to 0, current is 0, I equal to 0, and virtual short. This means this, and I equal to 0. This is what ideal op-amp means. Second, ask yourself, is there any feedback? How do we check for feedback? Go to output side and see if you can reach input from output. So I can reach, if I travel along this path, I can reach to the input side. So feedback, yes. Third, what feedback? What kind? So what kind of feedback do we have here? Since output is connected to negative terminal, we'll get a negative feedback. Now when you practice these questions, you will answer within 10 seconds. This is very simple. This is just because for the sake of practice I'm repeating them over and over, so that you get habitual to this. It becomes your muscle memory, right? So V1 is 1, V2 is 2. What is the value of V0? Again, very simple question. We'll do again the same concept which I applied before. KCL, KVL and nothing else. So current would be 0 here, current would be 0 here, and virtual short means the voltages would be the same at this point and at this point. And yeah, so current is 0 in this, so no current will go out. Fine, let's go ahead now. Okay, so let's write KCL at this node. So I'll say KCL at inverting input, inverting input, correct. So I'll assume current, this current is I1, this current is I2, and let's say this current is I3. So what does KCL say? Incoming current equal to outgoing current. So incoming current is I1 at this node, plus incoming current is I2, very good. Outgoing current is I3 plus 0. So this is no current is going here. Okay, so I get I1 plus I2 equal to I3. Very good. What is I1? Now in order to find I1, I'll apply Ohm's law across this resistor. Okay, note that this value Vx is equal to 0. Why is it 0? Due to the virtual short condition. Okay, so let's find the value of I1. So I1 can be written as Ohm's law across this resistor, V1 minus Vx divided by 2k. I2 can be written as V2 minus Vx upon 5k. This is 5k, this is given. I3 can be written as, I3 is Vx minus V0 divided by 4k. Very simple. Now I'll just write them. So V1 minus Vx upon 2k plus V2 minus Vx upon 5k equal to Vx minus V0 upon 4k. Now k gets cancelled, very straightforward, and we put Vx equal to 0 because this is a virtual short. So I'll get V1 by 2 plus V2 by 5 equal to minus V0 by 4. Note, Vx is 0, so it's minus V0. So I'll get V0 equal to minus 4 times V1 by 2 plus V2 by 5. So V1 and V2 are, the values are given, so you can simply put them minus 4 times 1 by 2 plus 2 by 5. This is minus 4. This is 0.5 plus 0.4. 0.5 plus 0.4 is 0.9 into 4. This is minus 3.6 volts. So the answer would be that V0 is equal to minus 3.6 volts. Note, we should pause here and explain one thing. See, this is V1. This is what this circuit is doing. It's adding V1 and V2. Note that it's adding V1 and V2 and then inverting it with some factor. Correct? So this kind of a circuit is also known as adder circuit. So this can be asked. This type of circuit, I repeat, is called an adder circuit. Why is this called adder circuit? It is adding the two input signals with a factor, of course, but yes, it is adding. So this type of circuit is called an adder circuit. Please remember this. In the previous question, what we had was, so let's look at this. I can write it as minus of V1 minus V2 by 2. Remember that what it's doing, it's subtracting V1 from V2. V1 and V2 are being subtracted from each other. This sometimes, not always, this sometimes somebody may refer to as a subtractor circuit. Okay, just please do not go into the nomenclature. I am just saying that this is a thing which you can observe. Since the two input voltages are being added, hence it can be called as adder circuit. And the negative sign comes because because the inputs are fed to the inverting terminal and we have a negative feedback. Okay, so I'll again summarize. As always, we were given an op-amp. It was an ideal op-amp, so we assumed that input current to both the inverting and non-inverting terminal was 0, as well as output current from the op-amp was 0. And we applied, and since it was an ideal, we applied the virtual short condition. So this becomes the same voltage as so Vx will be the same voltage as this, which is in this case 0. I simply wrote KCL at this terminal, at the non-inverting terminal. I1 plus I2 equal to I3. I put Ohm's law to find the expressions for I1, I2 and I3. I put the values. I put Vx equal to 0. V1 and V2 were given. So I simply can find out the value of V0. This is very straightforward questions. I am doing nothing fancy, just KVL. This is not even KVL here, just KCL. That's it. And just you have to remember that it's a virtual short condition. That's all. Right. Next question. Okay, so we have now for the first time we see capacitors. Now, can somebody tell me? Okay, how should I put this? What is the current through a capacitor? Okay, I'll draw here. So this capacitor is C, and let's say a voltage V in is being applied to this capacitor. So what is the current through this capacitor? Can somebody tell me? Let's say V.
So alternating current.
Yeah. So let's say this is the voltage that I apply. V in equal to V cos omega t. What is the current through this capacitor? IC. IC equal to what? Can somebody tell me this?
V in by reactance of capacitor.
Okay, very good. So V in by reactance. What is the reactance? Now you have to tell me that.
XC. It is 1 by
XC.
omega C.
Okay.
I omega c,
Yeah.
right?
Yeah.
So j omega c.
So it will be like this, correct? 1 by j omega c, right?
Yes.
Okay, this is one way of doing it. This is here, this is called, in we are working in the frequency, not in the frequency domain, but here we work in the imaginary numbers. So j is an imaginary here, iota, iota. Okay, this is other way of doing it. So because you must remember this q equal to cv, the very basic capacitor expression, right? So let's say I take differential on both sides. dq by dt is current, equal to c is a constant. So what do I get? The current through a capacitor is c dv over dt. Now both the expressions are correct, note that this is not wrong, I'm not saying that. While solving for expressions of current, because we are in time domain here, remember that. So when you are in time domain, go with this approach, that I equal to c dv over dt. If you are in frequency domain, use this. We'll see, we'll use this expression sometime later, but for now, today, because we are in time domain, remember question says we are in time domain, so we have, so it's better that we go with this approach. Excuse me for a second. Right, okay, so this is the thing. So again, our approach will not change, our approach will remain the same. Check whether the three steps. First, is it an ideal op-amp? So let's see, does the question say anything? Input voltage, no, nothing is said. Assume that it's ideal. Very good. Second, does it have feedback? What does it mean? Feedback means output, some part of output should be connected to input. Yes, there is. This output is being connected to this input terminal. Answer, yes. Third, what feedback? So negative feedback. Why negative feedback? Because output terminal is being connected to the negative terminal of the op-amp, so output is negative. Remember I told you negative. You see, every question is negative negative feedback. Why? Because this gives stable output, and all our results have been very stable. See, this was minus 3.6 constant value. This was, expression was given here, but it was a stable expression, it was not changing randomly. So yeah, that's that. Okay, so now we know what we need to do. Okay, so input voltage is being provided to us as 2 cos omega t. Output voltage is also provided, R equal to 1 kilo ohms. We need to find the value of C. Very good. This is the circuit, and these are the values that are given. Input is 2 cos omega t, where omega is equal to 100 radians per second. V out is 2 cos omega t minus pi by 2. Note a phase shift of pi by 2, which usually comes when there is a capacitor involved. R, this resistor is 1K, omega is 100 radians per second, and we need to find the value of capacitor. Again, the approach which is always there, since it's an ideal op-amp, I'll assume current here is 0, current here is 0, current here is 0, and virtual short. This means this is short. So let's assume this voltage to be Vx, this voltage to be Vx, and always obviously this voltage will also be Vx. Very good. So now, as I always do, let's apply KCL at inverting input. KCL at inverting input. Okay, incoming current, okay, let's assume this current to be I1, this is I2, this is I3, this is I4. Very good. So the incoming current is I1, this should be equal to I3 plus 0. Okay, so I1 equal to I3. Okay, what is the value of I1? Again, I simply apply Ohm's law. So Vin minus Vx, because this resistor Vin minus Vx upon the value of this resistor is R, equal to I3 Ohm's law across this resistor, which will be Vx minus V0 V out, that is upon R. Very good. Let me just simplify this. So it will be V0 equal to 2Vx minus Vn. Okay, very good. Now let's apply KCL at non-inverting input. KCL at, sorry, non-inverting input. Okay, so that would be I2 equal to, incoming current is I2, outgoing current would be 0 because no current is going here, plus I4. Let's write the expressions for I2. I2 would be Ohm's law across this resistor. So this will be V in minus Vx upon R. I4, okay, this I4 is nothing but current flowing through this capacitor. Now, what is the expression for current flowing through the capacitor? I derived it here. It is C dV by dt. Let's put this here. This will be C dV by dt. What is the voltage across this capacitor? Vx minus 0. This voltage is Vx, this is 0. So that's the voltage applied across this resistor. This capacitor. It will be C d Vx minus 0 over dt. Let's solve it a bit. V in minus Vx by R equal to C dVx over dt. Okay. Now we need to find the value of Vx in order to solve this expression. Otherwise, because C value can be determined only when you know Vx. Now we know Vx from this expression, so we can write 2Vx equal to V in plus V naught. Okay, the value of V in I can put from here. It's 2 cos omega t plus V out is 2 cos omega t minus pi by 2. So this would be 2 times of cos omega t. Okay, cos A minus B, cos A cos B plus sin A sin B. So this will give it to be sin omega t. As is applied, cos A minus B equal to cos A cos B plus sin A sin B. So it will give me sin omega t. This implies, so 2 gets cancelled, so it will be cos omega t plus sin omega t. Very nice expression. Let's put this expression here. Okay, so I'll get V in. Okay, let's also put the value of V in here. So V in is 2 cos omega t. Let me change my pen so that it's clear what I'm talking about. Okay, so we put this value here. So we get 2 cos omega t, that's the value of V in, minus Vx. Vx is cos omega t plus sin omega t divided by R equal to C dVx over dt. I'll solve this, don't worry. So what we get is, so one cos gets cancelled, so we get cos omega t minus sin omega t over R equal to C times, now let's differentiate dVx. Okay, so when we differentiate dVx, we'll get the differential of sine, cos is sine, so we'll get minus sine omega t. The differential of sine is cos plus omega cos omega t. This is what we'll get. Okay, or cos omega t minus sin omega t divided by R. I am taking omega common, so we'll get omega c multiplied by minus sin omega t plus cos omega t. Now LHS and RHS are same as that numerator, this term, the trigonometric term. So this will get cancelled with this. I'll get C equal to 1 divided by omega R. The value of omega given in the question is 100. The value of R is 1K. This will come out to be 10 to the power minus 5 farad. So this comes out to be 10 to the power minus 5 farads. This implies 10 microfarad. Do we have such option? Yeah, we have this option. Option C. Alright. Again, I'll summarize the results. This was an ideal op-amp. So again, input currents are 0, output current is 0, and we have a virtual short condition in a negative feedback circuit. So what I do, as I always do, I apply KCL at inverting input. I get this expression. I apply Ohm's law. Then I apply KCL at non-inverting input. I get this expression, and then I apply Ohm's law here. But here, since this is a capacitor, so you can just treat it as like a counterpart to Ohm's law for capacitor. So I put the values, and then rest is algebra. So I find the value of Vx from this expression. I put it back here, and then I just take a differential, cancel the terms, and then finally replace the values what we have. Omega is 100, R is 1K, we get 10 to the minus 5 farad, which is 10 microfarad. Straightforward question. What we learned from here is that when the capacitors are involved, there will be always some differential term or integral term depending on the question. So, right, but you also note that there was a phase shift. So, whenever there is a phase shift, input and output, this implies either there must be a capacitor or inductor. Resistors do not give a phase shift. You must remember that. Resistors, no phase shift. Sorry for that. No phase shift. Right. If there is, I repeat, if there is a phase shift, there has to be a capacitor or inductor. Okay, moving forward. Next question is, this is from 2015. Very straightforward question. This is a question which is directly asked. Okay, so can somebody tell me what is this circuit? Is this an adder? I'll give 4 options. Adder, subtractor, integrator,
Integrator.
or differentiator. Okay, now I'll ask you, how did you claim that this is an integrator?
Because here the capacitor is there, so.
No, it can be differentiator also, right?
Because in capacitor, generally we do integrate to finding the current. That's all. I thought.
Okay, no, this is a differentiator. See,
Oh.
I don't remember this. Whether it's an integrator or differentiator, I don't remember. What I do is I know KVL, I know KCL, I know Op-Amp. Okay? That's the only 3 things I know. So based on that, I'll solve the problem. That's it.
Yeah.
You don't have to remember it, because I told you every question I am doing the same thing. KCL at inverting input, KCL at non-inverting input, and Ohm's law. That's it. Nothing else. I'm not even changing the approach. Last class we did 5 questions. This class I'm doing 5 questions, and in the next class also my approach will remain the same. I just have one approach. That's it. It solves every problem of Op-Amp every time. Okay, let's move forward with this. Okay, circuit is shown, RC equal to 1. Okay, input is given. This is the input. We need to find the output. Okay, very good. Again, step 1. Is it ideal? Does the question say something? No. Assume it to be ideal. Second, is there a feedback? Yes, there is a feedback.
Negative feedback.
Yes, feedback is yes. And the answer that it's a negative feedback because output is talking to the negative terminal. Okay, this is all that we need to know. Ideal. So let me go to the next slide because there's space problem here. Okay, right. So again, ideal op-amp, I equal to 0, I equal to 0, and virtual short means this is same as this. I'll change the pen once again, sorry. Right, let's assume this voltage to be, okay, this voltage will be 0 because this is 0, but my practice is I always assume to be Vx. Okay, so but coincidentally here Vx is equal to 0 volts. Okay, again let's write KCL at inverting input. Let's do that. Incoming current, let's assume this to be I1, and outgoing current here is I2, so it will be I1 equal to I2 plus 0. No current is flowing here, right? I1, we just talked about in that current flowing through a capacitor is I capacitor equal to C dV over dt, where V is the difference between positive terminal and negative terminal. So I write I1 equal to C dV by dt. dV is Vi minus Vx over dt equal to I2. I2 is nothing but Ohm's law here. So Ohm's law would be Vx minus V0 over R. Very good. What do we get here? Okay, Vx is equal to 0, so I can simply write dVi over dt equal to minus V0 over R. V0 is minus RC dVi over dt. Right, this is the expression. Note that there is an RC constant naturally, and we are differentiating the input voltage and inverting it also. Due to this feature, this is called a differentiator circuit. Differentiator. Why differentiator? Because this circuit differentiates whatever you are providing at the input and also inverts it, right? So now but that was not our problem. RC is 1, so let's forget about RC here for the time being. So our expression is this. Note that RC is equal to 1 was given in the problem. So, and we need to find out V out. Okay, V in is given to us, right? So let's find out the V out. So it will be, this is nothing but slope. This is Vi versus t. This x-axis is time. So we will do Vi versus t. Okay, so let's find out the slope between t equal to 0 to t equal to 1 seconds. What is the slope? dvi over dt is the slope. So I'll find dvi over dt. This is a straight line, so I can say final minus initial. So y2 minus y1, as you know, y2 minus y1 over x2 minus x1. y2 is this, y1 is this, so this will be 1 minus 0 upon 1 minus 0. This is 1. Okay, so v0, but it's an inverting sign also, so the slope is 1. So the value that this implies, the value of v0 would be minus 1 volts. Okay, let me draw it here. I'll use a different pen for drawing. Right, for between t equal to 0 to 1 second, the value is negative. This is V output. This is time. Right, so this is minus 1. Okay, this is minus 1. Right, now let's now do from t equal to 1 second to t equal to 2 second. Let's find out the slope. So dvi over dt, again same formula. This is a straight line, y2 minus y1 upon x2 minus x1. Now y2 here would be this because this is the final point, and y1 would be this. So y2 would be 0 minus 1, 0 volts minus 1 volts divided by time is 2 seconds minus 1 second. So this will be minus 1. So v0 is nothing but minus dvi over dt. So this will have to be minus 1 into minus 1. This will have to be plus 1 volts. Okay, so from 1 to 2 seconds, what we are getting is plus 1 volts here. So this is like this. These are straight lines. Sorry for the bad drawing. This is 1 volts. Again, this is a positive slope. So again, it will be minus 1 volts here, like this, and like this, and like this, and like this. So we'll get this square wave. Obviously, if you differentiate a triangular wave, you will get a square wave. Right. Okay, so this was our answer. So it was, it's a square wave, but initial value is minus 1. Let's see which option fits. Square wave, so this option gets eliminated. All three these are square, and initial was negative, so this gets eliminated. These two are negative, but our value was minus 1, so B is the answer. This is our answer. Remember, the value was minus 1 that we got, starting with negative square wave and value of minus 1. This is what we got here, negative value of minus 1. This is called, again I'll summarize. So we had here was an ideal circuit, this circuit, and we needed to find the value of V0 for a given input V in. Again, I did KCL and inverting input, assumed it Vx, this current is 0, this current is 0, and a virtual short condition. We derived that V out is minus RC times dVi over dt. Since input is getting differentiated, we call such circuits differentiator circuits. Then there's nothing but, since Vi was given as a triangle wave, if we differentiate a triangle, which I did here, you get a square wave. So this is what we got. And the sign is inverted naturally because we are putting the input at the inverting terminal. Remember that. So sign is always be inverted. The phase shift will always be there between input and output of 180 degrees if you are providing the input at inverting terminal, which we clearly see due to this negative sign here. Okay, right, this is differentiator circuit. A counterpart to this is integrator circuit. This was asked in 2014. See, 2014 they asked about integrator, 2015 they asked about differentiator. They are repeating the questions, just slightly changing the problems. Okay, so the input is okay. Ideal is given as always. Ideal Yes, question itself says ideal. Second, feedback. There is no circuit here, remember. So you must, this paper assumed that you must know what the integrator circuit is. We'll see what the integrator circuit is and we'll answer this question, but the answer is yes, and it's a negative feedback. I'll draw the circuit on the next slide, don't worry. And the input is given and we need to find the output. Just like this, we were given, just like this question, we were given the input and we were required to find the output between these four options. Here again, we are given the input and we are required to find the output. Right, let's go into the question now. This is the circuit that we have. Again, this is an ideal op-amp. This is 0. This is okay. This is the circuit for an integrator. I should say this first. This is the circuit of an integrator. How does a circuit of differentiator look? It looks like this. Sorry, this is capacitor. Both are negative feedback. V out, V in. This is a differentiator, which we solved in the previous slide, and this is integrator. We'll see why this is called integrator, because you must have a hint now. This integrates whatever you are providing here. Let's see, let's derive this. Just don't go on my word, we'll derive this. So current would be 0 here because this is ideal, 0 here, current is ideal, virtual short, assume this voltage to be Vx. Very good. Now let's solve the problem.
Sir, Vx itself is 0.
Sorry?
It need not to.
It need not.
Vx itself is 0. Or
no. See here, V0 was not 0. You see here? I assume this node to be value Vx. This is not always 0. You see in this problem it was 0 here. Sorry, it was non-zero here. We saw that, right? Vx was this is the expression. You see?
Yeah.
So Vx is not 0.
Okay.
I am just assuming this to be Vx. If this is grounded, then only it is 0. See, it's not grounded here. We have provided input here also. So here it's not 0. Here, since it's grounded, you see this is grounded, so this is 0. In this problem it's not 0.
Yeah.
So we see it was cos omega t plus sin omega t. Yeah, this is a good question actually. Some people just like, because if you're not clear, then you'll always assume to, which is not the case. Vx is just a voltage that I'm giving. This is just named Vx, right? Okay, so now again, as I always do, KCL at non-inverting input. Okay, let's assume the current here is I1, current here is I2, and current here is, which you see 0. So incoming current is I1, this is the incoming current. Outgoing current is I2 plus 0. So let's write the expression for I1. I1 is nothing but Ohm's law across this resistor. So I'll write V in minus Vx upon R. I2, again we derived that the current flowing through the capacitor is, IC equal to C dV by dt, where voltage is measured from positive to negative terminal. Remember this, in the direction of flow of the current. So current is flowing from here to here, so I'll write C d by dt of V. V is but this, so Vx minus V0. This is V0, this is Vx. Okay, so I get V in minus Vx upon R dVx minus, I should have, right. So Vx is 0 here due to virtual short condition, so I can simply say V in divided by R, this is 0, this goes 0, minus V0 over dt. So this will get V in over R equal to minus C dV0 by dt. This implies dV0 equal to minus 1 by RC integral of V in dt. Correct? So I get V0 equal to integral dV0 minus 1 by RC V in dt. That depends on the terms actually. So depending on limits you put, so you'll get some expression. So why it's called an integrator? Because the input voltage is being integrated to get the output. Hence the name integrator. Very simple. Earlier we saw, where was it? Yeah. If you differentiate the input, you get the output. Hence this circuit is called differentiator. On the other hand, if the circuit is designed in such a way that you need to integrate the input voltage to get the output voltage, you get such a circuit is called an integrator circuit. Very good. Now what was the voltage that was given to us? So this was like this. So this was the voltage that was given to us. I'll just confirm once. Yeah, correct. This time is T0. This voltage is, I'll not call this V0 because it will get confusing. Let's call it what should I call it? Let's call it VZ. Some constant voltage. This is V in with respect to time. We need to find the output voltage. V out with respect to time. This is what we are required to find. Now we know that V0 is integral of V in divided by minus 1 by RC. Okay, so you can clearly see there is a phase shift, negative factor, which is makes sense because this is being fed at the inverting terminal, so that makes sense. Okay, so let's integrate between I'll change the pen again. So let's integrate between, so let's integrate from t equal to 0 to t equal to t0. Let's see what values we get. So I'm using just this expression, so it will be dv0, let's call it at v0 and let's call it a vt0 equal to, what do we get? We get minus 1 by RC dv in dt. Okay, the value of v in, sorry, not dv in, v in dt, the value of v in is 0 here, so RHS becomes 0, so we get vt0 minus v0. This is the initial value of v0, so we get vt0 equal to, so it will remain constant. So whatever the voltage was there earlier, it will remain constant. Now we don't know what was the voltage earlier. That's the problem. So let's assume it was 0. It may not have been 0. I don't know what it was. It could have been everything. I am just assuming it to be 0. We'll see that it does not make any difference. We'll see that. Just have patience. So this is the first step. Now second, now we integrate from t equal to t0 to some general time t equal to t. Again, I'll use the same expression that we had derived. So we get integral of dv0 equal to v in dt. Now the limits are t0 to some general time t, so it will be vt0 to some general value. Okay, this was 0, correct? Yeah, to some general output v0. So LHS will become v0 minus vt0. This is equal to, now v in, what's the value of v in? V in is some constant vz. It will become vz dt t0 to t. This will become v0 minus vt0 equal to, vz is a constant which comes out and becomes t minus t0. Note that this is a straight line. This is an expression for a straight line. Please note that there's nothing happening here. Okay, so there's minus 1 by RC also, sorry, minus 1 by RC, minus 1 by RC, right? So what's going to happen is that so what we should get is we should get a negative slope. So you see that just check the term of t. The coefficient of t would be minus v2 upon RC plus this would be, this is vz t0 by RC. This is v0 minus vt0. Vt0 we assume to be 0, so the expression comes out to be v0 t times minus vz upon RC plus vz t0 upon RC. I'll write in the next page, don't worry. The value of v0 we obtained was t minus vz upon RC plus vz t0 upon RC, right? I'll draw the curve again. So this was your input voltage, this is vz, this is your v in voltage, this is your time, this is your output voltage that we are drawing, and this is again time. We assumed till here, till time t0, this is time t0, that this is 0. So this is 0 here, and afterwards it has a negative slope. So negative slope would be, this is positive slope, right? Like this. Yeah, this is negative slope, correct. So this is our answer. The output voltage should look something like this. Now I assume that this is 0. It can be anything, it doesn't matter, but it should be the feature should be like this, constant and then a negative slope. Let's see which of the options have this answer. Right, constant and the negative slope. So this is not there, this is not there, this is also not there, this is also not there. So no options are correct. Sometimes it happens, none of the option is correct. This is the closest one, but again, this is as I told you, there has to be a shift of the slope has to be negative, the slope is positive here. So if this graph were like this, then this would have been the answer, but otherwise this is not the correct answer. So yeah, this is how it is. This was an integrator circuit. Why was it called an integrator circuit? Very simple, because the output, we could get output by integrating the input circuit. The negative sign here denotes a phase shift of 180 degrees, which makes sense because we are feeding the input to the inverting terminal. That's it. Yeah, that's all I have for today. Okay, so let me stop presenting. Is not the negative terminal inverting? Yeah, negative terminal is inverting input, Maitri. If I spoke anything else, then I'm sorry for that, but yeah, negative terminal is the inverting input. Yeah, correct. Have I been saying, I've been saying that, right? Yeah, okay. Anything else? Okay, there's one more before we finish. There's in the next class also we'll be doing op-amps, but it will have slightly we will talk about bandwidth. So it will slightly complex, but again not too complex. Will be, as always I've been just doing very simple formulae, not formulae even, just very simple expressions that I'm doing KVL, KCL, and we'll continue with the same thing. So there's nothing to be concerned about that. We'll carry on with our sessions. These have been very good sessions for me, at least. Hopefully you are also learning. So yeah, any doubts you have, please ask me. All good?
Sir, what is the use of saturation voltage?
It's not about the use of saturation voltage. It's okay, I'll share again. Okay, so where is it? Yeah, here. You see, using this differential amplifier, we created an operational amplifier. Remember this, always remember this. So this circuit uses two inputs, VCC and VEE. To drive this circuit, we need two voltage sources. Usually these are power sources that we need to in order to drive the current in this circuit. So this is your plus VSAT, this is your minus VSAT. So it's not like we use them in order to drive this operational amplifier. So this VCC is this Vs plus here, so I can write that VCC corresponds to VSAT plus and VEE corresponds to VSAT minus. These are important. Without these, your circuit will not be driven. And these are the maximum voltages that can be provided in your circuit. See, let's say this is 15 volts and let's say this is minus 15 volts. The maximum that you can go is plus 15. Otherwise, there will be no current flowing. If this voltage is, let's say, plus 15, there cannot be any current flowing here. So the maximum voltage that you can achieve is plus 15. Similarly, let's say if this voltage is minus 15, this is also minus 15, there can be no current flowing here. Very simple. So that's what we mean. These are the maximum limit that have been put to us. The operational amplifier cannot go beyond this. As simple as that. These are the maximum limits, hard limits that you cannot go beyond. Like particle in a box, you cannot for infinite potential well, you cannot jump outside the potential well. Treat it like this. These are the hard limits. You cannot push them. So the maximum output can be provided, which I showed you here. The maximum output is plus minus VSAT. Positive VSAT on the positive VSAT on the plus VSAT on positive side and minus VSAT on the negative side. That's what we mean by these terms, saturation voltages. It cannot go beyond this. We also saw, yeah, you can see this here. Even if you apply whatever voltage and input, you cannot go beyond saturation, because otherwise the BJTs in this circuit will stop conducting. In this circuit, BJTs will stop conducting if beyond 15 or minus 15 volts. That's the idea here. Okay.
Okay, sir. Thank you.
Yeah. All right. Where is it? Okay. So yeah, that's all from me today. Yeah, any doubts, or we'll wrap up this session. Next session again, op-amps. Slightly we'll get one more step from here, and most likely we'll talk mostly about bandwidth. Next week only I have 3 questions, so if you have any doubts regarding op-amp or some previous topics, you can ask. I'll try to explain whatever concepts I have, because the concepts might get somewhat lengthy in the next class. So as always, we'll always focus on the problem, and I'll always summarize the problem after solving it. So okay, if you have no other doubts, then we'll wrap up. Thank you very much everyone for listening.
Thank you, sir.
Thank you, sir.
Goodbye, good night.
Thank you, sir.
Yeah, welcome. Thank you for attending.
Thank you, sir.